Accelerator Offload Functions presentation. Welcome to SNIA's xPU Accelerator Offload Functions presentation today. This is going to be a very informational and exciting event for us all. I'm your moderator, David McIntyre. I'm the Director of Product Planning over at Samsung. With me, I have four very distinguished guest speakers. Mario Baldi, who is a fellow over at Pensando Systems. John Kim, who is from NVIDIA and also the SNIA NSF chair. Yadong Lee, who's a principal engineer at Intel. And Dr. Joseph White, who is a fellow at Dell Technologies. So I am very excited to hear what each one of these gentlemen have to share with us today. So first, let me give you a quick snapshot at SNIA. So we have over 180 industry-leading organizations in our organization. We have 2,500 active contributing members and 50,000 IT end users and storage pros worldwide benefit from the great content and leadership that SNIA provides. You can learn more at snia.org/technical and also follow us at Twitter at SNIA. Here are some of the technologies that we cover, from networking, various standards, protocols, the whole mixed bag, to storage, soup to nuts, from hardware to software-defined storage, the protocols that support storage, and also securing the data. This is very important to SNIA as well, making sure that your data is secure and safe. Just a legal disclaimer that the content that is presented here is copyrighted by the SNIA organization. Feel free to access the material. In fact, you can do that at the tab, where you can access the Bright Talk tab and then access that material. There are no warranties express or implied, so please use at your own risk. But I think it's a great risk to take. There's a lot of great information that you're going to learn today. So this is a three-part series on xPUs. Our first webcast was SmartNICs to xPUs. Why is the use of accelerators accelerating? Well, we covered what the heck is an xPU. Well, we went into detail on that. We talked about trends and example workloads, deployment solutions, and also the market landscape. And if you didn't have the chance to catch it live, please look at it at this following link here, and you can watch it anytime you like on demand. So for today, we're covering the second out of the three-part series, and it's all about offloads today. So each of our distinguished speakers will walk us through network offloading, security offloading, storage offloads, and close with compute offloads. So with that, let's kick it off with our first speaker, Mario Baldi, who will talk to us about network offloads. Mario?
Thank you very much, David, and welcome again, everyone. As we said, we start looking at what network functions we offload to xPUs and what are the implications of that offloading on xPUs. So when we talk about offloading network functions, we can start from very basic functionalities, which are the ones that you typically find in a NIC. So when you want to put an xPU in a NIC, you will have to be able to interface with the host, be able to send and receive frames, and then also support those functionalities that are still typical of classic NICs, but a little bit more advanced, like handling segmentation and handling quality of service, consequently having multiple queues in your NIC. Things get a little bit more interesting when you want to provide support for virtualized environments. In that case, the xPU is going to be used for switching, for offloading the virtual switch that usually is running into the hypervisor. So in this case, your xPU will support solutions like SR-IOV. And what is interesting is that now in the xPU, you can have a hardware switch. So basically that switching that was originally performed in software within the hypervisor can now be performed in hardware at high performance. And similarly, you can support quality of service, not just for having multiple priorities for the traffic that's going in and out of the network interface card, but also for local traffic that's being switched between offloads. And in this case, you may want to have fairly complex scheduling algorithms. And again, what you can leverage here is specialized hardware for those complex schedulers, which would not be available when the scheduler was implemented in software in the hypervisor or consequently in the host CPU. And then when you want to support virtualized environment, you may want to support VLANs, microsegmentation, namely being able to separate workloads even if they are in the same logical IP subnet, and apply policies on the traffic between those workloads, no matter where they are, that you can that the xPU is going to evaluate and consequently apply. And again, increasing the level of sophistication of the offloads we want to have, we can go and offload gateway functionalities. In this case, the xPU has the role of a full-fledged layer 3 endpoint, and it's going to terminate tunnels that you may want to use to implement overlays. So, for example, support software-defined networks, or tunnels that you may want to use to support security. So either at the IPsec level, in which case you may want to implement either tunneling solutions or the transport mode encapsulation, or you may want to support the offload of TLS. TLS, again, enables us to create secure sessions, but is heavy on the CPU, and so we can offload it to the xPU. And by the way, I forgot to say, when you want to implement a tunneling solution, you may need also control layer functionalities, which are less heavyweight in the case, for example, of IPsec or TLS, but they are pretty heavyweight in the case of overlays. You may want to run BGP on your xPU. So that's not a functionality in the data path that gets offloaded, but still it's a pretty heavy functionality that's taken over by the xPU. And then going up in the sophistication, we may want to offload to the xPU the full stack of certain solutions. For example, you may want to offload the whole implementation of TCP to the xPU. So a TCP requires memory and processing to handle sessions. And if you offload it to the xPU, the CPU of the host will not need to reserve those resources and will be able to use it for the actual workloads that are running on the CPU. And along this line, one may want to offload to the xPU the whole RDME stack, which can be leveraged for example, in HPC applications. When you have in the xPU TCP or RDMA fully implemented, you can also consider offloading the full storage stack of NVMe over Fabric, and we'll talk more about this in the section on storage offloading. And finally, another very important network functionality that one may want to offload to the xPU is observability. Being able to collect, extract telemetry information, both on the system itself in which the xPU is running, about the NIC, or about a switch if the xPU is running on a switch, or about an appliance if the xPU is running on an appliance, or about the traffic, the packets. And then this telemetry can be exported with flow-based solution like NetFlow or IPFix, or with packet-level streaming telemetry solutions like INT, in-band network telemetry, or in situ OEM, which is the ITF variant. Another important aspect of observability is being able to capture packets and transfer them to a collector using, for example, ERSpan, or even better, given that the xPU has processing power and it's very sophisticated in the functionalities it can execute, you can use the xPU to locally monitor the traffic or the telemetry that you are collecting and possibly aggregate it so that it doesn't need to be exported in its entirety, generating a lot of traffic, or even use it to apply intelligence and detect anomalies and consequently generate alarms when an anomaly is detected. So now, given the various functionalities that we can export, how do we do that? That we can, offload, how do we do that? First of all, we have to consider that various xPUs will include different components. And in the previous webcast, we already touched upon the various components, hardware components of an xPU. We can have general purpose processors, we can have fixed function logic, programmable logic, application-specific processors programmed, for example, using domain-specific languages like before. And then we can have modules like schedulers, memory. So all of these elements can be present in xPUs. They don't have to be all present in all xPUs. Different xPUs may decide to include a subset of those based on design decisions or based on the specific use case that they want to address. But the interesting thing is that when we want to offload network functionalities, we may leverage different components, a subset of these components. And the other interesting observation is that even when we are thinking of a specific functionality, let's say TCP offload, we can decide to do it, to implement it in different way. We could, for example, implement it fully in a general purpose processor or fully in programmable logic or in a combination of a general purpose processor and an application specific processor. So both the hardware designer and the software designer have various options on how to offload network functions. And those options can lead to different performance and also to a different way of optimizing resources. Using certain elements rather than others can optimize the utilization of resources and enable the offloading of more functionalities. In fact, when we go and look at real use cases, what we can see of network offload, what we can see is that usually we don't need to offload just one function. Usually we need to offload multiple functions. And the deployment of an xPU to offload network functions, as well as the other type of offloads we will talk about later, it's usually not a one step. It's usually a journey where we start maybe by porting to a general purpose processor on the xPU software that we already have to implement those functions running on general purpose processor on x86. And then we progressively move part of the functionalities to other to other computational units like fixed logic or programmable logic or application-specific processors. And this will allow us also to free resources on the general purpose processor that we can use for porting new functions or to perform management functions, we said before, aggregating data or control plane functions. And in all of these also, we have to keep in mind that what is important in xPU when we offload network functionalities is the memory, the amount of memory. Because in xPUs, usually when we use xPUs is because we want performance and we want scale. And often we want to implement stateful services. So we need a large amount of memories where we can have large data structures that are possibly writable so that we can keep state. And with all of this said, I leave the floor to John for addressing security offloads.
Thank you, Mario. All right, as he mentioned, I would like to talk about security offloads for an xPU. So I think the first thing to talk about is that the networking capabilities, or the network, the ability to be inline and perform networking and do switching on the server for traffic both between the server or device and other devices, as well as for traffic between virtual machines or containers on the device, allows the xPU to perform a lot of security functions just by being in the network path or in control of the networking. So for example, the xPU can route or inspect or modify packet headers for security purposes, as well as for SDN or software-defined networking purposes. So for example, if it sees traffic coming in, which looks suspicious, it can inspect it, and if necessary, it can divert it. It can or block it and just drop the traffic. So for example, if there is a denial of service attack, the xPU could identify it as such and simply drop all the packets from that attack, instead, so that the server or the device doesn't have to deal with that traffic. If necessary, it can also rewrite or encapsulate or decapsulate the headers on the traffic coming in, which both is important for things like overlay networks or virtual networks, but can also be used for security purposes as well. The xPU can also run security software or security software functions, or both. So you can have things like a next generation firewall, a load balancer with a web application firewall, intrusion detection and prevention systems, or microsegmentation software. And these different pieces of security software, they can run on the CPU of the server and have the networking done by the xPU. They can run on an external server, with a control plane, but still, again, assign the xPU to perform some of their security functions on that device. Or in some cases, the agent or part or all of that security software can run on the xPU itself, because most of the xPUs have some kind of CPU cores, like ARM or MIPS cores, or RISC-V cores, and also have different accelerators that specialize in networking and I/O. So just being able to manage the traffic or inspect the traffic gives you the ability, or control the traffic, gives you the ability to run a lot of security functionality from the network side on the xPU. And second, there's the ability to do encryption. Mario mentioned this briefly, and I apologize that I forgot to update these diagrams, but let me talk through the different use cases. So first is the ability to encrypt and decrypt network traffic. So of course, the basic encryption itself is an important task. Concerns about privacy or data interception or data security are leading to more and more applications and users wanting to encrypt the traffic between 2 points. And so an xPU can typically do this potentially at 3 different levels. At level 3, you have IPsec. At level 2, you have MACsec. And at the upper level, at the application layer, sort of levels 4 through 7, you have TLS as the ability to encrypt traffic like web traffic or application traffic. So the first benefit is, of course, just the fact that this traffic is encrypted while it's passing between 2 servers or 2 devices or 2 appliances. But the second is that when you encrypt or decrypt traffic on the xPU, that allows you to inspect or modify or switch that traffic in the xPU, where if you left it encrypted, you wouldn't be able to. So again, if the traffic is encrypted all the way through and a regular network card is just passing it, the network card really can only see the top layer or outermost headers of the packet and cannot see inside or do anything else with what's inside the encryption. But if you terminate the encryption on the xPU, you then have the ability to inspect or route or switch or redirect that traffic with it to a different VM or a different container or a different device, and things that you wouldn't be able to do if the encryption were not terminated on the xPU. Second is the ability to encrypt and decrypt storage. So this storage could be a hard drive, it could be an SSD, it could be persistent memory. And so this means that as the data goes to the storage, it's being encrypted by the xPU, and when you read the data back, it's being decrypted in real time by the xPU as well. This functionality, of course, could be done in software with the CPU, but moving this to the xPU, both types of encryption, the network encryption and the storage encryption, gives you usually a performance advantage, and it frees up the CPU cores so that they can do what they usually do best, which is running the actual applications instead of having to do encryption and decryption. And finally, the xPU can help with accelerate key management. So what I intended here is for an illustration showing that typically when you set up an encrypted session or secure session, there is a key exchange that goes through between 2 different points. And for example, if you want to prove their identity, then you can send something with a private key, and then the receiver can use the corresponding public key to decrypt that. To verify that the machine or the application sending that data encrypted with the private key is who or what it says it is. So again, you can send the private key and verify the authenticity or origin with the public key. Likewise, if you want someone to be able to see something and only the proper recipient to be able to decrypt something, you can encrypt the data with the public key and send it, and only the person with the correct private key can decrypt that data. So this type of key exchange is very common whenever you set up an encrypted connection or secure browsing, or if you want to verify the authenticity or identity of something. And an xPU has the ability to accelerate this key exchange. It can also store the keys. So you have the ability to have the keys coming from a key server or a key management application somewhere, but then the keys can be stored temporarily in the xPU to accelerate verification and decryption or encryption of data. And some xPUs also have additional functions like a random number generator, which is important for setting up key exchanges in the first place, because using a true random number generator helps ensure that outside parties are not able to predict or replicate the keys for that exchange. That's 3 ways that xPUs help with security on the encryption side. And I think for my 3rd slide, there is the monitoring and telemetry. Mario already talked a little bit about this as observability, and I think he made a great point showing that the xPU has visibility into the traffic, not only in and out of the device or the appliance or the server, but also has visibility to traffic between virtual machines or between containers that are on that server. And normally an external firewall or external inspection device or external switch cannot see the traffic going on between the virtual machines or between the containers inside the server. But an xPU can, and that gives it the advantage because it's able to see all the traffic inside the server and outside the server, going in and out of the server, as well as accelerate that traffic so it can monitor more of the traffic more quickly without burdening the CPU. And then that traffic either can be mirrored or inspected, and a subset of the traffic or alerts based on what it sees can then be sent out to management applications or security applications or monitoring or telemetry appliances. So this gives the ability for the xPU to act as a telemetry agent, as well as providing other remote management and remote monitoring, like the ability to reboot the server if there's a problem, or the ability to interact with the server's BMC in order to check on server environmentals and as well as perform remedial actions if the server appears to be compromised. And that leads me to my 4th and last slide, which is that an xPU provides some security isolation. And this isolation is both from a performance standpoint as well as from a security standpoint. So a typical case would be that normally if you're running your firewall agent on the x80 or on the regular CPU and in the regular operating system, if someone compromises that server operating system, there's a good chance they can disable or avoid or hide from the security software you have running there. But by running this security functionality on the xPU, whether it's a firewall agent or intrusion detection or just telemetry, it's isolated from the domain that runs the main applications and operating system. So if someone or something compromises the main part of the server, it's very unlikely that it will also be able to compromise or evade or hide from the security functionalities on the xPU. So this type of isolation, again, protects the performance of applications on the main CPU of the server, as well as increases the security of the server because you have that ability to run it separately. So a compromise of the server is very unlikely to be able to compromise the xPU security at the same time. And finally, you have some customers who don't want agents or they don't want virtual machines running on their server, but the manager, the IT department or the cloud hosting provider or the service provider needs to be able to run the security and management capabilities on that server. So a good compromise is the xPU lets you run that on the xPU. For the rest of the server, it doesn't look like there's an agent, but effectively that server does have an agent or security capabilities on the xPU, helping protect the network and other machines nearby. And finally, there are some specialized security functions. I won't go into those in detail, but some xPUs can perform some of these capabilities like secure boot, really accurate time synchronization, application verification, and as also mentioned, key exchanges, acceleration. Okay, that is the end of my section. I'd like to hand this over to Yadong Lee from Intel, who will talk about storage.
Thank you, John. So for storage offloads, I will talk about xPU storage usages first, just to provide a context for storage accelerations, and then talk about the compression and the data at rest encryption. After that, I will talk about NVMe over Fabric offloads, which includes both initiator offload and the target offload, and then briefly talk about storage stack offloads. So for xPU storage usages, I have 4 simplified pictures here just to illustrate the very well understood xPU storage usages. The first picture shows NVMe over Fabric initiator usage, basically adding xPU into a computer host, right? So this xPU provides all the networking offload, the security offload that we talk about, and here, I mean, we're talking about the storage offloads. It can include other infrastructure service offload as well. So this NVMe over Fabric Initiator usage model here, right, enables storage disaggregation in cloud, enables bare metal hosting. From storage offload point of view, you can see all the algorithms, which includes compression offload, crypto offload, hash CRC offloads, and I will explain why we need to do compression offload in this initiator use case as well in next slide. One more thing to note here, I'm using NVMe over Fabric, right? Just as the example here, you could see many different protocols. Even for the block interface, you can see some other alternative solution using whether block, whether SCSI. The second picture here shows local storage disaggregation. Different CSPs, different customers might use a different name. Very well understood. And the reference design is AWS Nitro SSD. Basically, the SSDs, right, from a host moved to xPU. So xPU become the central place to manage the SSDs. It provides NVMe virtualization layer. It can also fully leverage on the accelerators in xPU to do the inline crypto offloads, inline and deep CRC offloads. For compression offload in this usage model is very interesting. From a technology point of view, it's very challenging to do this because this kind of a design often need to provide very high bandwidth storage solution, right? But I believe the industry will figure out how to do this kind of inline compression as well in this kind of design over the next few years. The third picture is known as xPU-based JBof design. So here, basically, xPU is used as a standalone system, right, to implement a storage server. It's often called as JBof just because of the simple design and some of the trade-off between the complicated enterprise level storage feature versus the high performance, high bandwidth solutions. So in this picture, xPU provides storage data path acceleration. You can also see some PCI switch as part of the solution, which can be used to have a better thing out canonical mode drives to xPU. So here you can see all the algorithms used in a traditional storage server, including compression, hash, dedupe, crypto CRC, erasure coding. The last picture is also very interesting, which basically adds xPU into a traditional storage server. This is still in active basic development, and xPU is used for storage data path acceleration. But often it requires a software repartition to move the front-end processing, right, of your back-end storage stack into xPU to make best use of the accelerators integrated in xPU, and also to make use of the, SoC CPU core capabilities from xPU. From the storage offload point of view, here it includes all the algorithm you would expect from a traditional storage server, right, which includes compression, hash, dedupe, and crypto CRC erasure coding. So next, I'm going to spend a little bit of time to explain why we want to do compression offload on the host and initiator. When I say host initiator here, I'm trying to stay general, but in today's conversation, you can think about this is the xPU on the host side, right? So one of the change, which is basically the for cloud usages, right? it drives the data at rest encryption per tenant to host side. One of the consequences of this move is it reduces the compression ratio and reduces the dedupe opportunity on the back end storage server. The reason is basically once you do the crypto, right, do the encryption, the data looks more random. So the compression ratio is significantly reduced. So as a result, we also move this compression operation onto the host initiator side. So for block storage service, this is often very tricky. It requires innovation. The reason is for a block, right? If you do compression, the data length is changed. So how to make sure the backend storage stack still knows this, handle this is a very, challenging task. And some CSP may already figure out this already. But what I'm trying to do here is just to state the key requirements for this kind of operation. Basically, do the compression first, then do crypto, right, on the host and xPU initiator side. First, data is compressed and encrypted on host initiator, which is very obvious. The second requirement here is for security isolation. So no encryption keys should be shared among host and the backend storage server. And then for compressed data, we still need to enable dedupe at the backend storage server. So that's a requirement for the compressed data. The first requirement here is for crypto operation. So the identical data blocks, right, after crypto operation should give me the identical, cipher blocks to enable dedupe at the backend server, at least for a namespace, right, using a single encryption key. This requirement, sounds very obvious, but it's actually very tricky, especially for NVMe encryption algorithm. So the way that NVMe encryption works today is, in addition to the encryption key, decrypted key, right? There's also another key called LBA tweaked key. The motivation behind this LBA tweaked key is to make it to identical LBA blocks look different after the crypto operation. But that algorithm, right, is going to make dedupe almost impossible at the back end. So to enable dedupe at the back end, we have to basically tweak that key a little bit. Basically, actually, need to bypass the tweaked LBA key, right, in that whole encryption algorithm. So another requirement is more from xPU design and from system design point of view. We need a very efficient compression plus crypto plus hash CRC chain operation. This is very critical because xPU design often has a limited memory bandwidth. If you do this kind of operation in 3 separate operations, the memory bandwidth consumption will be so high, which become a bottleneck already, right? So this chain operation is very important for this kind of operation on the host initiator side. So the next slide includes the typical algorithm used for compression crypto CRC hash algorithm. So I'm included here only for reference purpose. Because of time limited, I'm not going to speak to details to each algorithm here. Next, I'm going to talk about NVMe over Fabric initiator offload. So I have a simple picture here trying to explain, different design choice and the different implementations. The first picture shows the existing way to do this NVMe over Fabric initiator. So basically, it uses a standard NIC, right, often known as a foundational NIC, FNIC, and the whole NVMe over Fabric initiator soft stack runs on a host. I'm using NVMe over TCP as an example here because NVMe over TCP consumes more CPU cycles, memory bandwidth, right? And if you do crypto CRC, which put more pressure on the host CPUs and the memory bandwidth. But with xPU, you can move this whole NVMe over TCP initiator, right, into xPU itself. xPU will expose this high performance PCIe interface, NVMe interface to host. So on a host, you just need to run that NVMe driver, right, which is another high performance driver, lightweight driver. So the whole initiator stack now is implemented in xPU. So it can fully leverage on the accelerators from xPU to do the inline crypto, inline CRC offload, which is more efficient. For TCP stack, the picture here shows, okay, keep TCP stack running on xPU CPU cores because that's the typical solution. But as Mario explained earlier, you can find the solutions, right, to have this TCP offload in hardware path as well. So basically, the functions of this NVMe over Fabric implementation, right, can be split across hardware and software in any combination, depending on the trade-off, performance, and the complexities in the design. The last picture shows this NVMe over RDMA initiator offload based on xPU. So typically you will find a hardware path design just because the RDMA solution usually done in the hardware path. So here it includes inline crypto CRC offload, right, which can provide, very high performance solution, low latency solution for this kind of xPU based initiator design. So that's the initiator offload to xPU. Next, I will talk about this NVMe over Fabric target offload to xPU. So as mentioned earlier, when it comes to implementation design, the functions of this NVMe over Fabric target implementation, right, can be spread across hardware and software in any combination. The key challenge here is basically build an efficient inline compression and inline crypto CRC offload in a data path. So I have two pictures here trying to illustrate the two typical solutions. The first picture on the left side is to run this target software stack, right, on the xPU SoC, but use the accelerators in xPU to do the offload. For example, compression offload, crypto offload, CRC offloads, right? This is often known as look-aside offload model. Basically, now the software is the control points and have to use accelerator, right, to do offloads. It's less performing just because of this look-aside offload model, but it's flexible because the software path, right, stays on the CPU cores, so it's easy for customization, easy for changes. Which is one advantage of this solution. The right picture here is basically trying to build a high performance solution purely in the hardware path itself. So I'm using NVMe over RDMA targeted hardware path here as an example. Here, often you will find a full hardware path solution which can do all the inline offloads and provides the lowest latency, highest performance. But often you also have to make some trade-off because once you put this whole thing in the hardware path, it's less flexible, less programmable. So depending on the requirements and the consideration, right? The requirements about flexibility versus the performance, you have to basically make some trade-off and choose the right solution for your specific use case. So that's target offload. Next, I will talk about this storage stack offloads. For the backend, the storage server, the software stack, right, usually is customer specific, and all the tier 1 CSP will have their own solution. So what I'm doing here is just use this open source solution SPDK as an example to explain some of the enhancement and changes we need to support xPU-based NVMe over Fabric offloads. So first, SPDK, right, is the storage performance development kit. It provides a set of tools and libraries for writing high-performance, scalable, user mode storage applications. So I have a simple picture here to show some of the key software components used for NVMe over Fabric solutions here. For details, please go to spdk.io. I'm not going to speak into each key component, but the architecture is also kind of very well designed, modular, easy for customization. You can add your own protocol, add some new enhancement, right? So we think SPDK is an ideal framework for xPU-based storage solutions. So first is a high-performance solution, also enables you to do everything, right, in the user space. It makes this, easy for customization, for changes, enable fast-paced innovation, which is very critical for cloud use case. So for NVMe over Fabric offloads, I'm using two examples to explain some of the changes and enhancements. The first, to support xPU-based NVMe over TCP initiator offload, we just need to add a very simple transport plugin onto this SPDK NVMe over Fabric layer. We call this as MPI transport. This is an NVMe protocol initiator transport. It's basically just a local transport to talk to xPU hardware interface, right? To configure the device, to get the commands, so it can flow through this SPDK stack here to make best use of all the software components we have. So it fully maximizes software reuse from SPDK. The second example is if you want to do this NVMe over RDMA offload, right, which includes initiator and the target offloads, one of the key enhancement we need to get this into SPDK is RDMA QP handoff. So basically, the RDMA QP is set up in the software path first, and then later handoff to hardware path, right? So this handoff flow is a little bit tricky, and we need to put this into SPDK so it can be used for both initiator offload and the target offload. Again, so this is just the one example, using SPDK as example to explain some of the enhancement and the changes for xPU-based NVMe over Fabric offloads. I think that's what I have for this storage portion. Next, I'm going to hand off to Joe to talk about compute offloads.
Hey, thank you. So we're going to talk about xPUs and computation. You've already seen references to this in our 3 previous sections, but I'm going to try to tie it all together and give a couple of different perspectives on the additional value of a DPU form factor as opposed to just a pure NIC form factor. So remember our definition from the previous session. An xPU is effectively a micro server optimized for data flow and packet processing, providing accelerators, offload engines, and local services. Okay, so I have a little schematic of an xPU. I think this is an idealized picture, and I'll use it throughout my discussion. Okay, so if we look at the architecture, why does this thing look like a microserver? Well, it's got ARM cores or maybe MIPS cores or some other core in the future. It's got hardware accelerators, coprocessors. It's got a NIC functionality. It's got a BMC functionality typically. And then it has packet forwarding and programmable pipelines with a management interface plus memory. That makes it look like a server. Okay. Typically, an xPU is built as a PCI card sitting inside of another hosting system, a full server, but it could also be an element of a intelligent switch or just a box with a bunch of xPUs to provide, power and kind of chassis management, for use as sort of standalone appliances. Okay. Because I'm running ARMs or MIPS cores, I can run Linux. Debian Ubuntu is quite common in the industry today, but any flavor could run. You could also run VMware on the xPU, or you could run proprietary. And then all of the common tool chains apply. Again, because this is an independent little system sitting there, I can use all of my management orchestration and control plane tool chains. And for the network configuration, I can use my network configuration tools. I have a switch in there. The switch will have network management APIs exposed. I can configure that thing directly. And then finally, I can use K8s for container installation and container management. There are a couple of different models. One is I could consider all of my xPUs a separate pool and manage those separately from the hosting system. I could, in theory, blend them. There are a lot of ways to apply K8s to xPUs. So let's look at some more detail around applications and containers. So you heard about networking, you heard about storage, including NVMe over TCP and NVMe over RoCE offloads, and you heard about security functions. Typically, those are built as a combination of a local application or an accelerator. But the application doesn't actually have to have anything to do with those. It could just be a general purpose application. It could be a control plane application, hypervisor offload. It could participate in AI ML model evaluation, especially if you have a card built with a GPU or adjacent card with a private bus for GPU. So I now have this hybrid device. I'm going to use the GPU pipelines for my AI model evaluation, and I'm going to use an app on or a set of apps on the xPU to direct and control the flow of information. I could do enhanced telemetry processing. So you heard in a couple of the other sections about some of the details of that. Here, what we're talking about is I run an app that consolidates telemetry or takes high rate telemetry coming off of the flows coming into the xPU, synthesizes that, extracts features, and then sends the features off to a central system, therefore thereby increasing my overall scale of telemetry and visibility processing. You heard Mario talk about some versions of network function virtualization. So if I have containerized network functions, I can run those here. And then firewall, key management, deep packet inspection, intrusion detection. So you heard John going through some of the details there. Those could run as parallel applications. Now, all of this parallelism means there's a fair bit of complexity. And again, this thing has a finite capacity. It's not like some, infinite magic bag of holding where I can keep just stuffing services in. But the point is that for any particular deployment or any particular system within the deployment, I can pick and choose the combination of services I want. In particular, once we get agreements on APIs and provisioning and lifecycle and container management defined within the Open Programmable Infrastructure Linux Foundation project, a lot of how you do that and how you mix and match will be standardized. And then, as was pointed out in one of the questions earlier, of course, the xPU itself will have to have fairly strong security if I'm going to use it in a flexible way, or you could install it as, hey, this is locked down. So a particular combination of hardware and software vendor could say, hey, here's a lockdown installation of a set of services, and you can't mess with it. And so there's a lot of ways. Again, there are a number of different ways you can combine these things. Now, a question was asked earlier about, hey, how does the host interact with this thing? So the host has a number of ways to interact. One is we could leverage, you can leverage accelerators directly from a hosting system application. So I need some compression done on a large chunk of data. Writing software to do that is certainly possible, but it's not the most efficient. I'd rather DMA it to a compression engine and then DMA the compressed result back. Same can be true of bulk encryption. You could do regular expression matching on a block of data. You could basically tell the DPU, hey, go comb through this data and use your regular expression matching engine. You can use P4 programs so I'd stream the data into the P4 pipeline. It does some transformation or calculation or matching on the data and sends me back the results. Okay. I could treat the xPU as a coprocessor, a full coprocessor, where I split the application between the hosting CPU and the ARM cores or MIPS cores on the xPU itself. Okay. I have memory access to and from the memory on the xPU and the hosting system memory. So DMAs can be quite efficient to move data back and forth. And then finally, we present standard PCIe functions where they exist. So if I present an NVMe drive emulated where it's really an NVMe over fabric drive or some more complicated set of backend drives that I'm representing from the DPU as a local NVMe, that's a great way to abstract. And then this thing becomes very much like an SCHBA in an IP SAN. If I add storage services to that, I can do some of the things that Yadong was talking about. If I present a NIC function, the hosting system goes, okay, I've got one or more NICs, and I can send and receive packets to them. If I had in the future memory access device, I could present that from the DPU. So the DPU can emulate and present a variety of PCIe functions. And then finally, of course, it could be an old school TCP offload engine as one of its functions. So, in the past, TOEs were maybe not cost effective because they didn't do a lot more than TCP offload and maybe a couple of other small things. DPUs or XPUs derive their value from the flexibility and the combination of services. And then finally, there's a very interesting concept that if I had a cluster of these things that were cooperating and collaborating, I could take host hardware and services and make those visible to some other application. So suppose I have a solution that uses GPUs intensively. And on one of my hosting systems, I'm not using GPU at all. And on the other one, I've completely saturated my local GPU. Well, I could build a GPU clustering and sharing system with XPUs, where the XPU can mediate the exchange, do the allocation of the resource, move the data back and forth, and transparently expand remote GPUs to augment local GPUs. So it's a very intriguing evolution of what you can do when you have kind of this intelligent coprocessor that's got heavy networking components and is plugged directly into your PCIe. So again, a variety of solutions and answers here. And with that, maybe we could take a few of the questions that have come up and then close out. What do you think, David?
Yeah, let's do that. That's a great idea. So here's one question. Since it can see traffic on the host, doesn't that widen the surface area for exposure if it was to be compressed? Compromised, sorry. Yep.
So this is John. I'll have a quick comment, though. Mario might also want to talk about it. Compared to running in the software on the server, no, it does not increase the exposure because it doesn't have really a wider view. Other than if it's decrypting or encrypting traffic, then it has a better view into the encrypted traffic. But compared to a switch, then it's a trade-off. If you have a switch. External switch would be able to see the traffic from many servers, the external traffic, but would not be able to see the traffic inside each server. So if a switch is compromised, it sees external traffic to a lot of servers, but none of the internal traffic. Where the XPU, if it were compromised, can see the internal traffic, but it usually only sees traffic to and from that server. It won't see external traffic to other servers.
Yeah, and I would add that as John was saying in his presentation, often the XPU is a hardened device. It uses secure boot. It only runs secure software in a secure way. So it is much harder to attack than the CPU.
Yeah, and another aspect of it's a question of who owns the control of the device and who's allowed to run software there. So if the organization that runs the infrastructure owns the XPU and controls the software that goes on there, and then it can act as a security boundary to the rest of the host, which might be running user software or other kinds of software. So I can use the XPU as a security check and a security boundary. So it actually could reduce the total attack surface or provide better isolation. Now, if I open up the XPU to be just kind of another general purpose microserver, then it has effectively the same attack surface as the hosting system. But I can run it in a mode or control it in a mode where I actually reduce the total attack surface and make that a security boundary. That's one of the interesting, notions that's come out in the industry recently about how XPUs can provide value.
Thanks, Joe. So here's another question. What are the specific offloads and functions that XPUs offer that NICs and HBAs don't provide today?
I can provide a quick comment, right, from storage offloads point of view. Basically, in addition to data path offload, because XPU has this integrated SoC CPU cores, so we move this whole storage application, right, which is basically one of the key service of the hypervisor infrastructure service move to XPU. So this is fundamentally different from previously just like a standard NIC or HBA based offload, because here we're talking about this infrastructure service offload. For that reason, we have this new terminology, right? XPU, trying to describe this is a new type of device. It's really offload some of your hypervisor functionality now onto XPU. So the host CPU can be totally freed up for hosting applications containers, VMs you may have.
Yeah, the big answer here is local switching, both on the PCIe side and on the network side, plus general purpose processors, plus the degree of programmability of the accelerators and the flexibility in the ways you can use them. That's kind of the high level summary answer.
All right. We have time for just one more question. So this one is about throughput. So when security offload is enabled, do we still need single flow 100 gigabyte per second rate? Can you talk about use cases where it might be needed?
Very short answer from my perspective, yes. If the DPU can support it, not all DPUs can support the encryption at the same maximum rate they can without encryption. But if it can't support it, yes, because you're running the same application, you just decided that traffic needs to be encrypted.
Okay, very good. So I think I wanted to spend just a quick moment to first thank our speakers for a job very well done. I know I learned a lot, and I hope you did too. And remember that you can access that content that was presented at the Bright Talk tab, where you can get the information on demand and review that at your convenience. So today is our second in the series of XPUs. Our third session will be XPU deployment and solutions, a deep dive. So we're going to go molecular. We're going to go to the fathoms of the XPU ocean and have even a deeper understanding on what we began to talk about today. So make sure to follow us again on Twitter at SNIA NSF, and to track the date and time of this third session that's coming our way. And thank you for attending. After this webcast, please rate the webcast and provide us with your feedback. It's very valuable to us. We have a very active group here that continues to strive for excellence, both from a technical and a communication standpoint. So your feedback is very well appreciated. This webcast and a copy of the slides, as I mentioned, not only in the Bright Talk tab, but also in the SNIA Educational Library at the following link. A Q&A from this webcast, including answers and questions we couldn't get to today. We got through most of them. I think we missed one. Those will be posted on our blog at sniasfblog.org. And again, follow us on Twitter at SNIA NSF. So with that, thank you again, and we look forward to seeing you to the third in the series of these webcasts on XPUs.